Questions about anything? Well, it's appropriate that Kate brought cookies today because it's a festive occasion. I'm going to prove the Cauchy theorem. Because we haven't been able to do it yet because I haven't talked about what a simply connected domain is. And so today I'll finally get to the definition, official mathematical definition of simply connected domain. But before I get to that, last time I defined what a homotopy was between curves with fixed endpoints. They start at A and they end at B. So two curves are homotopic. This is a definition that works for continuous curves. We're going to assume that our gamma naught and gamma 1 are piecewise C1 usually, because we're going to be integrating analytic functions along those curves. And in order to do that, they need to be piecewise C1. So gamma naught and gamma 1 might be piecewise C1. The definition allows them just to be merely continuous continuous curves. And the orange ones in between are continuous curves, okay, in the official definition. And so there's that homotopy that's a continuous function into the domain we're talking about on the square, 0, 1 cross 0, 1. And you think of the S as a parameter, and the T is the parameter for the curve, and S is another parameter, okay? So when S is 0, then the function of T that you get is the parameterization for gamma 0. And when S is 1, then the function of the T variable is the parameterization for gamma 1. Okay? And the ones in between are in-between curves. I drew a picture like this because it's easy, but those could go kind of into three dimensions. They could cross each other. They could bulge out and bulge back in and be weird. So the curves could go outside, bulge out, and come back in. But they have to be continuous, and they have to start and end in the right spot. Questions about what a homotopy is? Okay, well, I'm going to prove that the integral along those things doesn't depend on the curve when we had talking about analytic functions. And the feeling is if gamma naught is close to gamma 1 and f is analytic in the omega, then the integral along those closed curves should be the same. And if you wanted to prove that without doing anything new, think about two curves that are really close together. Then because the thing is there'd be a distance from those curves to the boundary, and so once you figure out what that is, you could stick little discs around like that and cover that picture with little discs. And then you see if I made little cuts like we do, I would get little curved linear rectangles, and I could integrate around those curved linear rectangles and add them all up and realize that along the cuts are going to cancel when I add them all up. And so when I do that little curved linear rectangle in the middle there, I'd be doing a Cauchy theorem on a convex set, because the little disk would be convex. And so that would be a closed curve in a convex set. And so the integral around that little curved linear rectangle would be 0. And if I add them all up, starting at A and going to B, the cuts would cancel. And so that's the feeling you should have for it. And so in fact, you could make yourself a proof for that feeling. Because if you look at this homotopy, you can make that grid small enough that all those curves were close together. And so the first orange curve is close to the green one, so that value would be the same. And then the next one is close to that one, so that value, and you could go all the way to the blue curve using that concept. So that's a perfectly valid way to do this whole thing. The problem is those curves in the middle are merely continuous. So we've got to grapple with that. But that's the feeling you should have. So I claim from a continuous homotopy, I can easily get a piecewise C1 homotopy. This is the first semester I ever resisted saying homotopy. Finally. Anyway, step one, we know how to approximate a curve in the plane by a piecewise C1. Mainly just take the little secant chords along there and make sure that the interval is chosen small enough that those things are close to the original curve and stay in gamma. And so that's an elementary thing to do. Let me write a formula for it. So I've got a z of t mapping an interval from 0 to 1 into that curve. I'm going to get a z twiddle of t that's piecewise C1 and close to it. Okay, and so on the interval from Tn to Tn plus 1, that's a linear function that connects the z of Tn at Tn to the other end, which is the z of Tn plus 1 at Tn plus 1. So that's a linear thing that does what I want it to do. Follows those little black chords. And so and they hook up. So that thing would be continuous, and it's piecewise C1, so it has kinks, but no jumps. Okay, so that's how I changed the definition to get a piecewise C1 curve close to my original, which stays in omega. Okay, so that's easy. Okay, now we've got that. I'm going to fix that grid above, the little rectangular grid, so that if you look at one of those little orange rectangles in the grid, it would map, the homotopy would map it to a curvilinear rectangle that's small enough and far enough away from the boundary that I know I can stick a disk around it. And a disk is a convex open set, of course. And I want it so the closed disk could be contained in omega. Okay? And that's by uniform continuity. So I'm using here uniform continuity of H on the compact set 0, 1 cross 0, 1. So that's the key facts I'm using for this thing. Anyway, that's the picture. And step 3 now, once I know I have that grid that's small enough, I'm going to do the piecewise linear approximation on the orange curves, only the orange curves. So let's see, that would be the t variable, and I'm going to replace the function on those orange curves by the piecewise linear one, basically. Okay? So I'm not doing it in between the orange curves, I'm just doing it on the orange curves. Okay, so that's the next step. And now that I've changed the definition just on the orange curves, I'm going to change the definition of H everywhere. And the idea is kind of like a homotopy. Well, this is the word homotopy. That's a homotopy between the left curve and the right curve. It continuously deforms, but fortunately, that homotopy is linear in the S variable. So I've got things that are linear in the t variable, and now I'm introducing something that's linear in the s variable. All right, and so I have L and right for left and right. That's the orange function. That orange function is that on the orange curve. It's piecewise linear, and so it's just a line on that thing. And I morph it from one to the other by doing the standard. I guess that's called a homotopy. Okay, and so that's the same principle as before. When S is equal to SNN, it's that thing on top in the numerator there, right here, is 0. And so when S is Sn, that would be the left phi sub L. And when S goes to Sn plus 1, I get 1 in that quotient. And then that term would kick in, and the phi L would cancel, and I'd be left with phi sub r. So that's a standard trick. So that new definition agrees with the things on the orange curves and morphs from one to the other in between. And it's continuous. In fact, it's linear on the inside of this, on the rectangle. So when I do that in each of the little things and realize they hook up, they might have a kink, but they hook up on the orange curves and the purple curves there. Or I guess that's magenta. So I get a new piecewise linear homotopy, and that's what I wanted to. Another things you might see in books maybe is if you start with a continuous homotopy, you can easily get a C infinity homotopy. And one way to see that is you can do, if you've ever seen it in a PDE class, convolving with the sort of Gaussian bump function. You can smooth out a continuous function and make it infinitely differentiable and stay close by. But all we need is a piecewise linear homotopy. We don't care if it's C infinity, but one could easily get a C infinity one if you wanted to think a little harder. Questions so far about anything? Let's see. So the big theorem is that if f is analytic on a domain and two curves are homotopic, of course these are fixed endpoint curves, so they both start at A and go to B, then that integral of f along those curves is the same. So that means that integral is path independent. So it's important to say here A and B are fixed endpoints. And so the integral is path independent. Well, the proof is going to be a snap. There's a copy of that picture to look at. I'm going to add up integrals around each of the little rectangles. Okay? And so H would take that little rectangle I've got there with the red arrows. H would take that little rectangle to a curvilinear rectangle, and I know my partition is fine enough that I could stick in a disk that's convex and far away from the boundary, like that, and apply Cauchy on convex set. And so if you think about the integral around that little thing, it's 0. And now you add up all those little rectangles and realize that all the orange and purple integrals cancel. Because if you think about it, they're all going around counterclockwise. And so when you add the one above, it cancels out the top, etc. And when you add the one to the right, it cancels out the right-hand side. And it does that all the way around. And so all the interior ones are going to cancel out, leaving you an integral around the outside. And the integral around the outside is an easy thing to compute, and it's what we're interested in. So the bottom is just a constant curve. And so, of course, the definition of that integral would be the integral of the constant f of a, and the derivative of a, which is a constant, d by ds, would be 0. So that's a constant curve. It always gives you a 0 integral. There's the calculation. The right side, remember, so that would be the parameterization would be when s is equal to 1, this would be the z1 of t. And I'm writing this as a partial derivative because it's a two-variable thing, but this is z1 prime of t. So that's just the definition of the complex integral. That's the integral of gamma along gamma 1 of f dz. The top is 0, 2, because that's a constant thing. And the left side, look at, well, let me go back up and look at it. It's going the other, the left side, I have the arrow there going the wrong way. I need to, if I'm going to go around this thing counterclockwise, that needs to go the other way. Okay, so, and of course we know how to parameterize the curve and get the minus of the integral. So the left-hand side should be minus the integral along that gamma naught of f dz. And so when you add them all up, you get that the integral along gamma naught equals the integral along gamma 1. Questions about that? So the important thing is that it goes the other way. This is gamma naught, and we need going the other way. So that's why I get minus that. So gamma naught corresponds to this piece in the rectangle. Okay, I guess that says it. Okay, we're done with fixed point curves and homotopy. Questions about it? Now I've got to talk about what it means for two closed curves to be homotopic. And then I can finally define simply connected. So two closed curves are homotopic if there's a homotopy. Here's the picture of the homotopy. It's going to go from the green curve and be like a rubber band and stretch and go to the blue curve, right? I like my homotopies to look beautiful like that, kind of like a ODE graph picture. But they could be crossing each other. They could be bulging in and out and then getting squished down. The feeling is it's like you took a rubber band and pulled it tighter until it clamped down on the other curve. Yeah, so the green rubber band, you would start shrinking it, and it would clamp down onto the blue curve, and that's what it would look like in the end. And those intermediate things are the stages. Okay, so when I stick in s equals 0, that's the gamma naught curve. When I stick in s equal 1, that's the blue gamma 1 curve. And the only thing I need for the curves in between, I need this thing h to be continuous on 0, 1 cross 0, 1 again. But the important thing instead of the fixed endpoints is that they be closed curves. So those red dots are that's the parameterization starting at t equals 0 and going around to t equal 1. Okay, so those are the starting and the ending points. And so those should hook up together. And so that condition is easy to write. I need the starting point to equal the ending point. So that simply says closed curves. So the closed continuous curves. Of course, I don't think I mentioned it, but my homotopy is H, once again, on 0, 1 cross 0, 1. So it's homotopic in omega, so that it's got to go into omega, and it's continuous. Well, the big theorem with exactly the same proof as the one I gave for the fixed endpoints is that if f is analytic on a domain and those two are closed homotopic curves, because of course the gamma naught and gamma 1 are piecewise C1 curves when I use this theorem. piecewise C1 smooth curves. Closed curves. Then the integral around f around those curves is 0. I mean, the same. So this allows to, let's see, that says an analytic on a domain. That domain could have holes. So if these two curves both went around the same hole, then and are homotopic, then those integrals would be the same. All right, and the proof is exactly the same as above. I would replace my orange curves with piecewise linear and do the homotopy thing and get piecewise linear homotopy. But then the difference is when I do the calculation in the end, the left and right side are my integrals of that I'm interested in. But if you think about the bottom curve, it's parametrized in the s variable when t is equal to 0. All right, so I see I made a mistake here. The function here would be f of that. Okay. Even though I made a mistake, it doesn't affect anything. And the d by ds of h0s would be, in the parameterization, because those hookups are the same, that would be the same as the bottom integral. But the difference is the bottom integrals going the other way. So the bottom's going left to right. The top is going right to left. And so I'd have to take minus the top if I was going left to right. And so because those things are equal at the end point, at t equals 0 and t equals 1, their derivative with respect to s are equal. So this equality is because h of 0s equals h of 1s. So of course when I take d by ds, that's the same. And so when I add those up, the bottom's going to cancel the top. So they cancel. And the left and the right ones are exactly the integrals I want. And when I add up all those little rectangles, I get 0. And so that's going to give me left equals integral around right. Because it's actually right plus minus left is 0. So that's the proof of that. And now I can finally define what I mean by a simply connected domain. So the definition is the feeling is it has no holes. And so if you think of a curve as a rubber band, it means, or a rope, you can shrink it. Every closed curve in the thing can be shrunk down to a point. So it doesn't get stuck on a hole. That's the feeling, the mathematical feeling. Okay, so a domain is called simply connected if every closed curve in omega is homotopic to a point, meaning you can rubber band it right down to a point. Okay, so being homotopic to a point means, I wrote there, gamma is homotopic to z naught. Z naught, that means the gamma naught curve would be given by z of t constantly equal to z naught. So that's a curve that just sits at z naught. And that's like pulling a rubber band down to a point. And I showed you above that when you got a constant function, the integral is 0. So if that curve is homotopic to a point, then the integral of f around it would be 0. So that's the Cauchy theorem. If f is analytic on a simply connected domain and gamma is a closed curve in omega, then the integral of f around the curve is 0. All right? And in this one, it's a piecewise C1 curve. And of course, we already proved that if we have fixed endpoints. That's the theorem we had before. We could deduce that fixed endpoint theorem from the closed curve theorem, because whenever you've got two fixed endpoint curves, you can go out by one and back by the other, and that's a closed curve. So that's a second proof of that fact. Questions about the Cauchy theorem? That's an exciting moment. By the way, in the definition of simply connected, the curves are continuous. But it doesn't matter if you make them continuous or not, because you can always replace them with piecewise C1 curves. But that's the official topology definition. And remember, all the theorems we proved on convex open sets now hold for simply connected domains. And that's because the tool we needed was those integrals being independent of path. So for example, in those basic theorems, we cooked up analytic antiderivatives. That was basically the most important thing. And I mentioned in previous things that whenever you know the Cauchy theorem, you get the same results. So for example, I proved back that you can cook up analytic antiderivatives whenever you know the independence of path. Remember how that went? By analogy with this convex case, it's natural to try to define an antiderivative as an integral along any old curve that starts at a fixed point A and goes to Z. Okay. The Cauchy theorem told me that that's well defined. That's the hard part. Once you know it's well defined, then you're set. Because if it's well defined, you can start and go to a center of a disk, Z0, and then take the line segment going from Z0 to Z and get yourself a curve that starts at A and ends at Z. And that one, we know that is an antiderivative for little f on that little disk. So, I'll write down the theorem here. Same proof I gave in the convex case now works for analytic antiderivatives on a simply connected domain. We can cook up analytic log functions. If G is non-vanishing and analytic on the domain, then there's an analytic f so that e to the f equals G. The feeling is that's like a branch of the log function, log of G, an analytic branch. There's no branch cut, but that's the feeling. Or if you wanted to sort of make a more general word for branch, that would be it. And of course, once you have a branch for the log, then you can cook up nth roots just by taking e to the f over n would be nth root of G. And the other thing I did using a antiderivative was that if U is harmonic on omega, I can cook up a harmonic conjugate on a simply connected domain. And that was because I could get an analytic function that looks like the derivative of U plus IV. And then if I find the antiderivative of that thing, it turns out the real part is f plus a constant. The real part is U plus a constant. Anyway, that proof works now if you go back and look at it in the simply connected domain. And I should warn you in that little fine print there that whenever omega has a hole, all four of those things can be shown to have counterexamples. Of course, some harmonic U would have harmonic conjugates, but I could cook up one that doesn't if it has a hole. Kind of like the log function. If you go around a hole, the next time you go around, the argument changes by 2 pi. That's the trick when you mess up stuff with a hole. Questions about that? Okay, let's see. This was so heavy on the drawing, I decided to do it in advance. Now I ran out of pre-prepared. I should give you some examples of simply connected domains. Examples of simply connected domains. Oh, let's see. One, I kind of like this one's kind of fun. I take a square, and then I go halfway and take a line that goes halfway. So that's it. This would be 0. This would be a half. This is a half. Okay. Now I've got from the halfway point, I go halfway to the other side. That would be at the 3/4 line. And I go 3/4 distance. So this right here would be 3/4. And I would remove that line. And this has length 3/4. This would be length 1/2. This would be length 3/4. Then the next one I would do would be what's this? 7/8. And this distance would be 7/8. And I keep doing that forever. That's a simply connected domain. And if I was going to show you a homotopy, I'd give you a closed curve in here. It would only go through finitely many of these things. Okay, there's a closed curve inside that region. So I'll put a ... here to mean you do this forever. How would I make a homotopy of that down to a point, if you think of it as rubber band? Suck it in like a piece of spaghetti, exactly. You know exactly how to do that. So you just pull it in and reel it in and squeeze it down to a point. That gives you the homotopy. So you could do that with your bare hands. That's the spaghetti homotopy. Suck it in like spaghetti. A closed spaghetti. And then the other famous, or there's lots of famous simply connected domains, is the Sierpinski snowflake. You could take an equilateral triangle, and then you start adding equilateral triangles on each. I don't know why I always do it. Looks good on that side. And then on each one of these, you put an equilateral triangle. I'm adding the interiors here, etc. You get this thing called the Sierpinski snowflake. It's a fascinating curve. And it's actually what's called star-shaped. Is it star-shaped? Oh, maybe it's... No, it's not star-shaped. But if I drew a closed curve like that, you realize it can't go into the little tiny things you add at some point. So it'd be infinitely many of those, and you could squish it, just suck it in to the origin. Anyway, it's not hard to show with your bare hands that the interior of this thing, so etc. That's a simply, and the interior of that would be a simply connected domain. It's a fascinating domain because it obviously has finite area, but if you try to make sense of the perimeter goes to infinity. And so the famous isoperimetric inequality is that the area is that the area is less than or equal to the perimeter squared divided by 4 pi. This area is obviously finite, but this goes to infinity for the Sierpinski snowflake. And so as you add points, anyway, that's one reason it's an interesting thing. So it's a mind-blowing fact. That's a bounded, that's not the whole complex plane. And so the Riemann mapping theorem is going to tell us that Sierpinski snowflake, there's an analytic map one-to-one onto the unit disk, which is conformal. That's a mind-blowing fact, hard to believe, maybe. And so if I asked you to show that there's a continuous map of that to the unit disk, you'd be hard-pressed to do it, even both of those cases, to come up with a continuous map that would map that one-to-one onto the unit disk. And so if you ask a topologist what the proof is, they'd say, oh, you just use the Riemann mapping theorem. Analytic functions are continuous. So that's kind of neat. Let's see. So another example, convex domains are, of course, simply connected domains. Convex. And so let's see if I had a curve in here. I'd pick a point A, and I would take what I would call the tornado homotopy. So I would just take intermediate curves that get pulled down to the point, etc. So these curves would look like the same copies but smaller and get sucked down to that point. Another another simply connected kind of domain is a star-shaped domain. So let's see, a star-shaped domain looks like this. There's a point, and pick any old point in here. The line connecting this point to that red one is in the region. So convex means any 2 points you can connect. Star-shaped means there's 1 point that you can connect to. Okay, so this is star-shaped. And of course, the tornado homotopy works for those too. You squish it down to that point. So the same homotopy. Well, here's an interesting star-shaped domain. Let's take the complex plane minus a branch cut. C minus the interval from minus infinity to 0 is star-shaped. Here's some topology facts I should mention. If you look at Alfor's books, which used to be the most common book on complex analysis. Here's Alfor's equivalent definition. Of omega in the complex plane simply connected. It is that you take the extended complex plane and subtract omega, and you get something that's connected. No whole, it's one piece. It can have holes. I mean, it won't have holes, but the extended complex minus omega is connected. That turns out to be equivalent. And so the feeling is that omega doesn't have any compact holes. Because if it did, then that'd be more than one piece if it had a compact hole. Anyway, the need for, if omega is bounded, you don't need that extended complex plane thing. But if it's unbounded, then you definitely need that. So remark, you need that extended complex plane instead of C when omega is unbounded. But you don't need it. C works fine for obvious reasons. When omega is bounded. And let's see, that maybe I have time to sketch the proof. That's number one. Number two, being simply connected is the same that any two curves going A to B are homotopic. So omega is simply connected is equivalent to, given 2 points in omega, any two curves that join those 2 points are equivalent. And gamma AB, gamma twiddle AB, then those are homotopic. Gamma AB is homotopic in omega to gamma AB twiddle. Let's see. I'm going to see it. What's the easy direction? I think this is the easy direction. So if I had a closed curve, I could start it at A would be the starting point of that closed curve, and this B right here would be Z of 1/2. And then I would take so this would be my gamma naught over here, and then this gamma 1 on the other side would be minus this curve. And then those two would be homotopic. So I'd get this. So I'd start at gamma naught and then go over to gamma 1. And so my feeling would be, as I move those over, the last one would look like this. I'd go out and back. The last one, and then I would suck it in like spaghetti. That would be homotopy. Okay. Anyway, yeah. Alfors has clever ways of doing this that use analytic functions. If you know about antiderivatives, then you don't have to do anything topological. But you could give yourself topological proofs by playing around with the definitions of homotopy and realize, oh, if I just go out and back in the end, I could suck that in like spaghetti, and I could write out the homotopy that would be the sucking in like spaghetti operation. Anyway, you can think about the other direction. For fun. Let's see, was I going to draw a picture? Let's draw a picture, why not? Well, let's see. So I've got a simply connected domain, which means the closed curve homotopy exists. So if I had two curves, here's my gamma naught, here's my gamma 1. I'd make a closed curve with a minus gamma 1. So use minus gamma 1, get a closed curve, and then I would do a homotopy of that closed curve. That would shrink down to a point. And how would I get a homotopy of curves? Well, I start here. There would be a starting point and an end point. So those would be these points along here. Okay. And those starting and end points would move. And so I would follow along until I got to here maybe, and then jump on this curve and go around until I get to the other side, and then follow that out. And as I extend those all the way to the middle, I would get curves that would eventually look like the black curve, going all the way. And I would do that from both sides, and I realized, I could go back by the other side. Anyway, if you can draw a picture and think about it, you can define the homotopy. It'd be agony to write out the details and formulas, but there's the picture. That's how you do it. It's kind of fun to read Alfors because he doesn't like to work hard. He thinks hard, but he doesn't work hard. Let's see. Another interesting thing is now that we know the homotopy trick, we can make sense out of the integral along gamma of f dz when gamma is merely a continuous curve. You just take a limit of like the chord curves approaching gamma and realize all those integrals be the same, and so that would give you a definition of the integral along gamma.